Next, I will briefly introduce the solution approach for this competitions. See cryptography direction POC challenge. First of all, this challenge implements a simple authentication system centered around AES-GCM, while also providing three functions: update, register, and login. Let's look specifically at the contents of this challenge class. Firstly, after the initialization, we can see that the key and AESG, CMS, AAD are both fixed and unchanging, but the nonce can be changed through update. However, we maintain a set to ensure that each new nonce hasn't been used before, and after updating the nonce, we set its counter to 2, meaning the same nonce can only be used twice. Subsequent register and login operations will decrease the usage count of this nonce. During the register process, we encrypt the user's username using AES-GCM, then concatenate the ciphertext and tag to form a token. During login, we only need to decrypt and verify the current token using AES-GCM MIF decryption and verification pass. We consider the decrypted username to have access privileges and can then provide access services. In actual usage, we completely reference the previously mentioned functions to provide some services. It's worth noting that the nonce is arbitrarily controlled by the user, but during registration, the platform randomly generates an 8-byte random string as the username. After registration, both the token and username are sent to the user. During login, our goal is to forge a token for the admin user, and after logging in, we can obtain the flag. To solve this challenge, let's first look at AES-GCM. Actually, AES-GCM adds an authentication process on top of the AES-CTR mode. Specifically, after encrypting the plaintext using CTR mode, we concatenate the plaintext with the previously mentioned AAD to get a long string. Then, based on this string, we divide it into blocks and convert each block into an element in the Galois field, thus obtaining polynomial coefficients for a polynomial. Then we use the current key to encrypt an empty string, converting this block into an element h in the Galois field. Substituting h into the previously mentioned polynomial yields a polynomial calculation result in the Galois field. This is actually what we call the GASH process. After calculating GHS, we also compute a J0 based on the current key and nonce. Adding this J0 to the previous GHAsh finally gives us our tag. We can see that in this process, with the same key or nonce, plaintext and AAD correspond uniquely to a specific ciphertext and tag. Here, whether you tamper with the tag or the ciphertext, our decryption cannot pass, thus providing an authentication function. Participants more familiar with AES-GCM may know that if the same nonce is reused twice, we can use its AAD and the Twokis texts to establish such a polynomial and its point values. This allows us to eliminate the influence of J0, obtaining a polynomial concerning h by finding roots of this polynomial in the Galois field. We can derive h. Then, by substituting this h back into the polynomial, we can obtain GHSH combined with the token. We can derive J0. That is, if the same nonce is reused twice, we can completely determine all unknowns, enabling us to forge a valid tag for any desired ciphertext. Here it's the same, although our nonce reuse count is limited. Each nonce can be used twice. Therefore, the first step of our attack is to call register twice for the current nonce, obtaining 2 tokens. Then, by executing the attack we just described, we can derive h. However, you might notice that I don't know the AAD here. Does that mean there's an additional unknown in this polynomial? Actually, no, as you can observe, Although I don't know the AAD, my ciphertext length each time, including the AAD length, etc., are all fixed. Therefore, all terms on the right side of this polynomial are known. On the left side, it's a constant unknown placed at the same position. That means the highest coefficient of my polynomial each time is a fixed unknown. Its effect on this polynomial is actually the same as adding a j0 to the lowest position after calculating the polynomial. Therefore, we can combine j0 and the unknown corresponding to AAD into the same unknown, then repeat our previous steps. We can still obtain a polynomial concerning h and then recover h. Here it's worth noting that during the polynomial root finding process, you might obtain multiple possible h values. However, we believe we have effectively narrowed h down to a very small subset, so recovering h is not problematic. After completing the first step of our attack, we have derived h, but why don't we try to find j0, or the variable combining j0 and a? Because after this process, our nonce has already been used twice in subsequent interactions. Whether register or login, they can only be performed on a new nonce. j0 is related to the nonce. After changing the nonce, we have a new j0, so recovering j0 at this point is meaningless. However, we note here that although j0 is related to the nonce, h is a value only related to the key. Throughout this process, our key never changes. Therefore, our previous solution approach only needs slight adjustment to fit this challenge. That is, using the first nonce, we can use the two tokens from the first nonce to derive h. Then on the second nonce, this h is equally valid. Therefore, on the second nonce, using one token and substituting this h allows us to derive the variable combining j0 and a that we don't know further. As we just said, all required variables are now obtained. If we still have one chance left, with the second nonce, we can forge it into the token corresponding to the username we want. Then proceed to login, achieving our goal. Specifically, how do we forge? Actually, we only need to because AES-GCM mode uses a CTR-like structure during encryption, and CTR is essentially a stream cipher-like structure. So if we perform some bit flipping on the ciphertext, such as XORing it with a mask, the XOR result is equivalent to XORing on the plaintext. Therefore, we can combine the ciphertext token obtained from the second nonce with its username by considering the difference between this username and admin. And XORing with this difference, we can actually obtain a valid token corresponding to admin. Then using this token to attempt login solves the problem and gives us our flag. In summary, the attack approach is roughly like this. First, we use the first nonce to attempt register twice, obtaining two tokens, then recover the AES-GCM key h. Then we update the nonce once as we wish and register once more under the current nonce, obtaining a new valid token. Then, using the currently known key h and the new token, forge a valid token corresponding to the admin user under this current nonce. Then, using the last opportunity of the current nonce, logging in with this forged token allows us to obtain the flag. This is the complete content of this challenge.